Hello class, welcome to this Unit 6 review. So we're going to go ahead and go over problems from basically the lesson numbers on here are 6.1 to 6.4 as well as 6.7. It does technically have some five and some equations, which is 5 and 6, but just it's kind of tied in with the other sections. All right, so let's go ahead and get started. So the first one is the graph shows 3 times, or well, there's not really a graph, but the function is f of x equals 3 times 2 to the x power. What are the domain, range, intercepts, asymptote, and the end behavior? So remember, if you wanted to graph 3 times 2 to the x, remember that the parent function for that is just 2 to the x. So if we were to just graph, this, you have to know that the graph of an exponential looks like this. And we know that this is a growth. This is an exponential growth because the b term here, b, which is equal to 2, is greater than 1. All right, so remember that the general exponential model, y equals a times b to the x, if b is greater than 1, it's growth. If b is less than 1 but greater than 0, it means a decay. Okay, so this is how it looks like if it's a decay. If it was a growth, I'm sorry, this graph in black is growth. Decay is the red graph. So if it were to be decay, it would look like the red. Okay. All right. So since we know that this graph is a growth, it looks like the black graph here, and we know that the asymptote of an exponential function is y equals 0. So this is my asymptote right here. So the asymptote is y equals 0, which is the x-axis. So we know that the asymptote is the x-axis. So basically, that gets rid of c, right? So it can't be c because it says the asymptote is the y-axis, which is not true. All right. Now, if we look at the y-intercept, the y-intercept is when x is 0. So we're going to plug in 0 into the original function. So we're going to do 3 times 2 to the 0 power. This is going to give me my y-intercept. So 2 to the 0 power is 1. 3 times 1 is 3. So that means my y-intercept is 3. So it cannot be d, right? Because it says the y-intercept is 0 right there, which is not true. All right, so now we got our y-intercept, we got our asymptote. Now we're going to look at the range, domain, and behavior. So the domain of this is all real numbers because you got all the x's on the left side, and you got a graph on the right side of the coordinate plane. So you have all the graphs on all the values on the left and the right side for x, which means that domain is negative infinity to infinity, or all real numbers. For our range, the smallest y value is 0, and then from there it goes up to infinity. So my range from bottom to top is 0 to infinity, and it does not cross 0. So we indicate that with a parentheses rather than a bracket. So this also means that y is greater than 0. So if we look at our range, we know that both of these have y is greater than 0, so that's good. They both have a domain of all real numbers. Now let's look at the end behavior. So as x goes to negative infinity, the graph actually goes down to 0. So for my end behavior, as x approaches infinity or negative infinity, y approaches 0. And as x approaches positive infinity, which means as it goes to the right, the graph goes up. So that means y approaches infinity. So the only one that satisfies that criteria is A. All right. So number 2, it says an initial population of 820 quail increases at an annual rate of 23%. Write an exponential function to model the quail population. What will the approximate population be after 3 years? So since we know that it is increasing, we know that it is a growth. So that means the general exponential growth model is written as y equals a times 1 plus r to the t power. That's the model for growth. So we know that the rate is 23%, and that's given by 0.23 as a decimal. We know that the time is 3 years. And we know that the initial quail population is 820, and that's my A. My A is the initial. So if we plug that in, we have our model is y equals 820 times 1 plus 0.23 raised to the t power, which if you rewrite that, that's the same thing as 1.23 to the t power on the inside of that parentheses. And then now you're going to plug in t equals 3 years into the function. So you're going to put it to the third power. All right, and if you plug that into the calculator, you're going to get 1,526 quail. So our answer is A. Number 3, in a particular region of a national park, there are currently 330 deer, and the population is increasing, so that's a growth, at an annual rate of 11%, so that's my R. So R is 0.11. A, which is my initial, is 330 deer. Population is increasing, so we're looking at a growth model. So we have y equals A times 1 plus 0.11 raised to the t power. So that is my growth model. I can go ahead and rewrite the 1 plus 0.11 and just change it to 1.11, and then that would be my final answer for part A. For part B, explain what each value in the model represents. Well, we kind of talked about it. This represents the Y-intercept or the initial, the Y-intercept or the initial population. This represents a 111% of the current population, or an 11% increase, basically. And then we have, an 11% rate, increase in the rate, so 11% rate. And then the t is the time in years. Okay, so then all we're going to do is plug in 5 years into that model. So we're going to go ahead and plug that in. Raised to the 5, and we get 556.07, but we're going to round that to the nearest whole number, so that's going to be 556 deer. All right, for number 4, without graphing, determine the function y equals 7 times 2/3 to the x power. And then determine whether it represents exponential growth or decay. Well, remember that you were looking at our b term, right? So our b term is 2/3. So b is 2/3, and that is less than 1, but greater than 0, which means that that is a exponential decay. Pretty straightforward. Now find the annual percent increase or decrease for the following model. All right, remember the increase or decrease is related to this, right? So that is saying that we're taking our 100% and we're adding 130% to that. Because remember our model was A times 1 plus R to the T. The 1 stands for the 100%. The R stands for the original percent. So basically the growth rate is 130%. And if you add that to 100, that makes 230%. So basically convert the 2.3 over to 8%. And that will give you a 230% increase from the original. So, all right. So without graphing, determine whether the function y equals 5.2 to the x represents a growth or a decay. Pretty straightforward. So remember, it's a b to the x. So the b here, the a is the invisible 1. The b is the 5.2. So b is 5.2, which is greater than 1. So it is a exponential growth. All right. So the half-life of a certain radioactive material is 71 hours. An initial amount of the material has a mass of 722 kilos. Write an exponential function that models the decay of this material. Find how much radioactive material remains after 17 hours. Round your answer to the nearest thousandth. Okay, so the general exponential model, right, is a b to the x. All right, so a is the initial amount. So we know that the initial amount is 722 kilos. So we start with that. And then we got to multiply that. Well, we know it's a half-life. So half-life means we cut it in half, right? So that means our b is equal to 1/2. That means you're going to cut the amount in half. So we got to times that by 1/2. And then we got to raise it to some power. Now, since the half-life is 71 hours, this means that after 71 hours, it will cut in half. So, so let's write it over here. So after 71 hours, you have 1 half-life. After 142 hours, well, that's 2 half-lives, right? So that's 2 times that you're going to cut it in half. All right. So basically, if you have 1 half-life, 2 half-life, 3, and so on, notice that if I double this, triple this, 71 hours, then that gives me more half-lives, right? So if I want to put an exponent here, if I want to put a random exponent, I got to take that exponent and divide it by the half-life. So if it takes 71 hours, then I know that 71 divided by 71 is going to be 1 half-life. And so that means that I have to cut 722 in half one time. Now, if 142 hours pass by, then I know that 142 divided by 71 is 2, which gives me 2 half-lives, which means that I have to cut this number in half 2 times. So this model makes sense right here. So in general, even though this is the exponential model, if you're looking at half-life, basically you can use a modified version of that model, and basically instead of using just x, you can use x divided by the half-life. Okay. All right. Oh, and instead of b, you could just use 1/2. Okay. So now we know that the a is the initial amount. For b, you're going to use 1/2. The power is x, and then you're going to divide that by the half-life time. All right. So we'll just tuck this equation aside for the next problem. So we got our model. So now we're going to take. We want to figure out how much radioactive material remains after 17 hours. So now I'm going to plug 17 in. So if I plug 17 in, that'll be 17 over 71 power. And then I got to figure out what that is. So I'm going to plug that into the calculator real quick. All right. And that's going to be 611.6. I guess we can use 589 kilos. All right, so that looks like B. All right, another half-life problem. So we know that we're going to be using the model, right? So we know that we're going to be using the 1/2 to the x divided by some kind of half-life. So the half-life is 32 days. Okay, so that's my half-life there. So x divided by 32. An initial amount of the material has a mass of 361 kilos. So we know that now my initial is A, 361 kilos. So there's my half-life model. And then find out how much radioactive material after 5 days. So now we're going to plug 5 into X. See, once you have the model, it makes it really simple. And then we're going to plug that in. So it looks like the one that has the X over 32, well, there's 2 of them that there's actually 3 of them that have the X over 32. So we got to figure out what's the right answer here. So we got 323.945 kilos. All right, so that looks like it's B. All right, so let's look at the next one, number 9. So these ones just involve graphing. So remember that the exponential equation is the exponential model, the general model is AB to the X. Now, if it's growth, right, which means if B is greater than 1, then it's going to look like this. If B is less than 1, or less than 1 but greater than 0, then it's going to be a decay, and it looks like this. Now, if it's reflected, so if A, assuming that A is positive. Now, if A is negative, then it's going to flip this model, right? So if A is negative, then in that case, this top one on the top left is going to reflect across the x-axis, and then it's going to end up looking like this. Now, if A is negative for the next one, for the bottom left, then it's going to reflect that across the x-axis, and then it'll end up looking like this. Okay, so those are basically the 4 cases where B is greater than 1, and then where A is positive. So A is positive on the left side, A is negative on the right side, B is greater than 1 on the top row, B is less than 1 on the bottom row. So those are all your cases. So if you know that, then you're basically good to go. So we know that the B here is equal to 1/3, which is less than 1. So that means it's a decay. And we know that the A is positive here, so you don't have to reflect. So since there's no need to reflect, this means it's a decay. So we're looking at this one right here. Now, of course, you can graph this on the graphing calculator. So I'll show you how to do one of these. So you're going to go to y equals, and you're going to type in the equation. So 8 times 1 divided by 3 raised to the x power. And then you're going to graph it, and it gives you the equation, of course, which is the one that we were saying earlier, the one that's going down like that. All right, so it looks like it's B. Next one's another graphing one, so we're going to fly through this one. We know that this one was a decay, so it went down. However, the A is negative, so that means it actually reflects across the x-axis, so it looks something like that. So the answer for that one is A. Number 11, we have another decay, so we know it goes like this. Now the 2 here indicates that it's shifting the function up. So that means that it's still going in the same direction, but it's shifted up 2 instead, okay? So that means that the asymptote is now going to be at the 2 rather than at the 0. So normally the asymptote is at 0, but now the asymptote is going to be at 2. So that's all it does, is shifts it up. So it's still going to be looking like it's going down, but notice that it's shifted up slightly. Okay, so that's going to be D. All right. So number 12, the population of turtles. Actually, we're not going to actually do this problem in class, but so we can cross this one out. However, I will show you how to do it, but we're not going to do this in the test. Okay, I'll show you how to do it, however. So if we wanted to do number 12, The population of turtles in a lake is estimated at 1,000. The population is projected to increase 12% per year. So that means that our model is 1,000. It's increasing, so it's 1 plus 0.12 raised to the t power. Okay, so t is in years. Okay, so this is in years. So now 1 plus 0.12 is 1.12. So this is going to be 1.12 to the t power. So this is assuming that this is in years. Now, it says which exponential function can you use to identify the monthly growth rate? So if I wanted to convert the t into months, well, in that case, I need to convert this into 12 over 12, because I know that there's 12 months in a year, right? So I'm going to change this, and I'm going to change that to 12 over 12. So it's still in terms of years, but now it's going to be in months because there's 12 months in a year. So it's 12 over 12. And now I can plug in the number of, I can plug in the number of months for time. Or I'm sorry, I can plug in, something for time, and then it will give me here the number of months. So if I plug in 2 years, well, then that's going to be 12 times 2 is 24 months, right? So basically it just converts it over to months. Now, what I'm going to do here, and the reason I did 12 divided by 12 is because that's going to equal to 1, and that doesn't change anything in the problem. So now what I'm going to do is I'm going to take this, I'm going to take the 12 here, and I'm going to bring it over to the inside. So if I do that, that'll be 1.12 to the 1/12th power. All right, so that's what I have. So now I know that I have 12t, and then see the 12, it's 1 over 12 because you got an invisible 1 on top, and then the 12 is on the bottom. So now this number here, we got to figure out what that is. Whatever, because that 1.12 to the 1/12th power is a number, is some kind of decimal. So let's figure out what that is. 1.12 raised to the, let me delete this, raised to the 1 divided by 12 power. And that will give me 1.00948. So 1,000, 1.0095 raised to the 12t. So now we got the exponential model for monthly growth rate to identify it, and so that's going to be C. Okay, but again, we won't go over that on the test, but just that was a problem in the lesson, but I figured I could toss that out. It's not really too important. Okay, so number 13. So how much money invested at 5% compounded continuously for 3 years will yield $820? When you see compound interest in which you're compounding continuously, you're going to use A equals PE to the RT. This is the formula for compound interest, assuming that you're doing it continuously. Okay, so the interest rate R is 5%, which is 0.05. Then you have the time is 3. Then the P is the principal, so that's how much you invested. You're actually looking for that. You're looking for how much you invested. So that's the P, that's a question mark. We don't know what that is. How much you yield, that's how much you get at the very end, and that's my A. So that's the amount at the very end. So our equation here is 820 equals PE to the, E is just a number, kind of like pi. And then we have 0.05 times time is 3 years. Okay? So in order to solve for P, I just need to divide off this E number, right? Whatever that E number is, we got to divide that off. So I'm going to go ahead and divide off by that E number. And then that will give me my P. So this is my P, but of course we're going to need to figure that out on the calculator, right? So we're going to do that right now. So we're going to do 820 divided by, we got to do second ln, that will give me E, and then 0.05 times 3. So it gives me $705.78. So $705.78. So it looks like it's D. All right. Credit card A is running a promotion where they'll charge 0% interest for the first year, 0.8% continuously after that. Credit card B has an interest rate of 0.7%, also compounded continuously. If you're going to make $500 of purchase and plan not to make a single payment for 2.5 years, which credit card should you go with? Write the equation showing the total balance at the end of 2.5 years for that card. All right, so let's break it up into the two credit cards. So on one hand, we got credit card A. Well, I'll call CCA. Okay, so for credit card A. So for credit card A, we have, remember they're compounding continuously, so that's going to be the Pert formula, right? So this is equal to PE to the RT. So now let's go ahead and plug in the numbers. So P is the purchase, right? So if you're making a $500 purchase, that's P. E is just a number, so we're going to leave it as E. The interest rate is 0.7 or 0.8% for credit card A. So you're going to have 0.8%, which is 0.008. Remember to move the decimal place twice to the left. All right, and then we're going to multiply that by the time, which is 2.5 years. However, because credit card A, there's a promotion where you don't have to pay for the first year. You're not paying for that first year, or you're not paying extra. So therefore, it's not really 2.5 years. It's really 2.5 minus 1 years. So it's really 1.5 years that you're paying it for. All right. Now for credit card B, our amount is, well, we still paid $500. We still purchased $500, the purchase price. And the E is now 0.7%, so 0.007. And credit card B does not have a promotion where you don't pay for the first year. So therefore we have to pay extra interest over the entire length of time, 2.5 years. So now what we're going to do is we're going to compare these two credit card amounts and see which one is less, and that's the one that we want to go with. Okay, so we have 500, and then we got second ln, that's E, and then to the 0.008 times 1.5. We're just going to call it 1.5 years. That's my first one. So $506.04. Now let's do credit card B. We're going to basically use the same expression but change the 7 or the 8 into a 7. Oops. Here, let me do this again. Change the 8 into a 7 and change this 1 into a 2.5 years. There you go. So now we have their new, so $508.83. All right, so you can see that even though credit card B has had less of an interest rate, you're still going to pay more because credit card A had that one promotion. All right, but it's not by much, but it's still a little bit better. So therefore, the best deal is the $506, which is credit card A. All right, number 15, you open a savings account and deposit $1,000. After 1 year of earning continuously compounded interest, your balance is that. We're also not going to do this problem. This problem is not going to be on the test, but I'll show you how to do it. So after 2 years, the balance is that. Okay, assuming you make no deposits or withdrawals, find the equation for the best fitting exponential function to represent the balance of the account after X years. How much money will be in the account after 10 years? So basically, we are going to use A equals PERT, right, because it's continuously compounded interest. Now, this time they tell us two amounts, right? So after 1 year, the balance is that. So let's write that in for A, because that's my A, okay? And this is my principal, P. This is how much I invested or deposited. So we have for year one, we have $1,018.16 equals $1,000 for principal, e to the, and then the interest rate, we don't know what the interest rate is, but we do know that it's after 1 year. So we have this times 1 year, okay? And r times 1 is just r, so I'm just going to write it as r, okay? All right, so now for year two, it's the amount is now going to be $1,036.66. That is a 6, not a 3. And it's still going to be 1,000, but it's going to be 2 years. So it's going to be 2 times r. So now what we're going to do, if we want to solve for r, we're going to go ahead and divide both equations by each other. And that will ensure that I get rid of the, what we'll do, let's go ahead and divide both equations. That will cancel out the 1,000. And then we can divide the 1,018 divided by 1,036. So let's do that. So that's 0.982 equals. Now remember, when we divide two things with an exponent, we're really subtracting the exponents. Okay, so really we're doing e to the r minus 2r power, and then r minus 2r is negative r. Okay, so this really on the right side becomes negative r. So in order to solve for in order to solve for r, I need to do the ln of both sides. The only way to get rid of an exponential is with a log. So I need a log base e, otherwise known as ln. Now those cancel. So now I got ln of this equals negative r. I can go ahead and divide the negative 1 on both sides just to get rid of it, and that's going to be my r. So we're going to figure out what that is. So ln of the previous answer divided by negative 1. And that gives us 0.018. Okay, so my r is 0.018. So now we know where our interest rate is. So if we use the Pert formula, which is 1,000 e to the r times t. So that's my new model. Now we know that that's our model. Now we're going to go ahead and figure out what money is going to be in the account after 10 years. So now we're going to plug in 10 in for t. So this becomes 10. Let's go ahead and change that to a 10 years, and then we can get our equation here. So we got 1,000 times e to the 0.018 times 10. So $11.97 and 22 cents. All right. So which one does that match up with? Looks like it's C. All right. So we're going to write the equation in logarithmic form. So remember that the purpose of the log is to retrieve the exponent. So what we want here is to actually retrieve this exponent right here. So in order to do that, we need to get rid of the 125. So what we're going to do is we're going to take the log base 125 on both sides. All right, so now the log base 125 and the 125, notice that the bases match, so they cancel. So now we have 4/3 equals log base 125 of 625. So it looks like our answer is C. Now number 17, we want to do the same thing. So we have 2 to the 5th equals 32. The only way to get rid of the base of 2 here is to do a log base 2 on both sides. So now they cancel, leaving us with 5 equals log base 2 of 32. So it looks like B. All right, so if we want to do the reverse and convert it to the exponential form, what we have to do is we have to take the base of the log into account. Okay, so in order to get rid of this log, I need to use an exponential. So I need to exponentiate both sides. So now in this example, the base of the log is a plus b, and we're doing the log of c, and that equals 16. So what we have to do is take the base of the log, and we're going to use that as the base to our exponential. So we're going to do a plus b raised to both sides power. That's the only way to get rid of the log, is to use an exponential here. So now this cancels, leaving me with c equals a plus b raised to the 16 power, which looks like d. Or not d, I'm sorry, c. Or c equals that, so a. So we're going to do the same thing here. So we have log base 4 of 1 over 16 equals negative 2. So the base of the log is 4. So we're gonna exponentiate with 4 as our base. So 4 raised to that power, 4 raised to that power. So now what we have here is we have 4 raised to the log power equals 4 raised to the negative 2. And now since these bases match, they cancel, leaving us with 1 over 16 equals 4 to the negative 2 power, which in this case is d. All right, the pH of a liquid is a measure of how acidic or basic it is. The concentration of hydrogen ions in a liquid is labeled with the bracket notation H to H+. So this stands for the concentration of hydrogen ions. So use the formula pH equals negative log of the concentration of hydrogen ions to find the pH level to the nearest tenth of a liquid with a hydrogen ion concentration of about 6.5 times 10 to the negative third. So all you're going to do is plug this number into the pH formula, the formula for the power of hydrogen. So we get negative log of 6.5 times 10 to the negative third power. We're going to plug this into the calculator and get an answer. Let's do that right now. So we're going to do negative, you have to include the negative here, so negative log 6.5 times 10 raised to the negative third power, and then close the parentheses. Let's double check my work here. Oh, this should be a negative key. I think I used the wrong key there. Okay, there you go. So and they want you to round it to the nearest tenth, so that's going to be 2.2 for my pH. So that indicates that it's acidic in this case. Quite acidic, 2.2. All right. So for number 21, if we want to evaluate the log, we can actually type this into the calculator, but we can also do this using a little bit of mental math. So what we do is, to show our work here, we're going to set this equal to x. Okay, so I'm going to write this off to the side here. So now what we're going to do is we're going to get rid of this log. Remember, the only way to get rid of this log is to use the base to exponentiate with that base. Okay, so we're going to do the base of 5 raised to both sides. So now this cancels. So we got 1 over 625 equals 5 to the x power. All right, so now we got to figure out, well, this number is flipped, right? So since it's flipped, this is a fraction. What I need to do is I need to figure out, well, okay, 5 to what power is going to give me 625? Well, I know 5 times 5 is 25. And then if I did another 5 times 5, that's another 25. Turns out that 25 times 25 is 625. So this is 5 to the 4th power. There's 4 5s here. However, since it's a fraction, we're going to make x into a negative exponent. That way, if we have a negative exponent, this means we flip it and it makes it 1 over 5 to the fourth, and then it gives us the fraction that we want. Okay, so in this case, x is negative 4. Now you can also type this into the calculator, but I would first show your work so that you can get to this stage, and then at that point, if you want to use a calculator, you can. Now remember that if you wanted to type this into the calculator, so let's say you wanted to type log base 5 of 1 over 625 in the calculator. So if you want to type this into the calculator, you're going to have to use the change of base formula. You're going to have to take the log of the argument divided by the log of the base. Okay, and that's how you're able to calculate log base 5. So we're going to go ahead and show you that calculation. So we have log 1 divided by, let me do it again here, divided by log of 5. Okay, and that gives you negative 4, which is the exact same answer that we got earlier, using a little bit of mental math. All right. Again, we're going to do the same thing here. So if you want to type this into the calculator, you're going to do log of 243 divided by log of 3. Log of the argument divided by log of the base. You can also use ln. ln will also work and give you the answer here. So you don't have to use log if you don't want to. You can use the ln key. And I go ahead and show you that with the ln key instead. So if you did ln of 243, divided by ln of 3, and you're going to get 5. So answer is 5. All right, so now, number 23, use natural logs to solve the equation. Round to the nearest thousandth. Okay, so let's say we wanted to solve number 23. We have 8e to the 4x plus 8 power equals 15. So in order to solve this equation, we need to get rid of the 8 on the outside. So we need to divide that off. So we're going to divide the 8 off on both sides. So now we're left with e to the 4x plus 8 equals 15 over 8. Now to get rid of the e, I need to do a log base e on both sides. Okay, log base e. That's the only way to get rid of an exponential is with a log. However, there's a name for log base e, and that's the ln. Okay, so we're going to use the ln on both sides. Okay, so there's a little invisible e there, and so they match and cancel. So we have 4x plus 8 equals ln 15 over 8. Now we can go ahead and subtract the 8 on both sides. And then we can go ahead and divide off the 4 on both sides. All right, so then when we do this on the calculator, make sure to put the numerator in parentheses. So we're going to do that over here. So we have parentheses, ln 15 divided by 8, close parentheses, minus 8, close another parentheses, divided by 4. So we get negative 1.84. Which is over here. All right, next we're going to solve number 24. E to the x equals 200, or 3 over 4. So all you got to do is get rid of the e. So you're going to do the ln of both sides, and that's literally all you have to do. So x equals ln of 3 divided by 4. So we'll go ahead and do that here. So we get negative 0.288. Looks like it's A. All right, number 25. Okay, go ahead and do it over here. So we have 6e to the 4x minus 2 equals 3. All right, if we want to solve this equation, we're going to have to move the 2 over to the other side. So I'm going to go ahead and add it over. Now this, I got to get rid of the 6 next, and that 6 is multiplying, so I got to undo that by dividing both sides. Now the only way to get rid of the e is with an ln, so I'm going to do the ln on both sides. Then the only way to get rid of the 4 is to divide off the 4. All right, so that's my x. We're going to go ahead and type that in, get our answer. So we have negative 0.046. All right. So number 26, we want to go ahead and graph the logarithmic function. So all we're going to do here is we're going to actually graph it using the graphing calculator. Remember that you can graph this using a table of values, but we're just going to show you how to plug it into the graphing calculator and get the answer. So pretty straightforward here. What you want to do is remember that there is no log base 2 key. So if you want to do the log base 2 of x, if you want to type the log base 2 in, remember you got to do the change of base formula. So you got to use the log of the argument, which is x, divided by the log of the base, which is 2. And then you can go ahead and subtract the 3. Okay, so that's how you're going to be able to type it in. If you don't type it in like this, then you're going to get the graph incorrectly. Okay, so it won't really work out in your favor. You won't be able to match it to any of the multiple choice. Okay, so let's go ahead and show you that on the calculator. So again, you're going to go to y equals, then you're going to type in log of x. That x looks a little weird. Let me double check something. Log of x. Okay, yeah, that's fine. Divided by log of 2, and then minus 3. You can go ahead and graph it. And there's our function. So in this case, it looks like it's approaching the y-axis, and it looks like it starts to cross the x-axis at about 8. Okay, so that means that we're looking at this graph right here. It starts to cross right about 8, which is what we want. Okay, so the answer is C. Now, if you wanted to do this graph real quickly, without having to, like if you wanted to do it quickly without having to use a graphing calculator, well, just keep in mind that the log base 2 of x, that's the inverse of 2 to the x. So if you know how 2 to the x looks like, you basically know how this looks like. Remember that 2 to the x looks like this, right? So then if you reflect that about the y-axis, or about x equals y, or y equals x, then you're going to get, something that looks like this graph here. Okay, and then of course, the minus 3 means it's shifted down, so it's going to be shifted the downward version of that. So it's going to be very close to it. All right, that's just a quick trick for that. But again, for the test, we're just going to, test your change of base formula skill there and plug it into the calculator. All right, so in order to do log base 5, we're going to do log x minus 2 over log of 5. All right, so all we got to do is plug that in. All right, so now, in order to actually plug it in, remember you got to type in the y equals, and then of course we're going to clear this function out. Go ahead and type it in, log x minus 2 divided by log of 5. And even though it's not showing you that it's approaching something, it actually is, right? It's approaching this asymptote of 2. So this graph really is, trying to go down, 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 even though it's not showing you your downward trend here. There is a downward trend, and then it's going up, all right? And it's crossing, at this mark here, the x-axis. So it's crossing at about 3. All right, so it looks like we're looking at A. All right, number 28, we want to go ahead and solve this logarithmic equation, and we want to round to the nearest 10,000th if necessary. So we'll go ahead and write this out on the right-hand side. All right, remember that if there is no base written for the log, we assume that it's an invisible 10, okay? So we're going to go ahead and write out the invisible 10 there. And the only way to get rid of the log is to take that base and raise it to both sides power, okay? So we're going to take that base, raise it to both sides of the equal sign. And now these match, right? So here I'll write out what the new equation looks like. So we have 10 to the log power equals 10 to the third power. Now these match. Notice that these bases match, so they cancel, leaving me with 4x plus 10 equals 10 to the third power. Now 10 to the third power is just 1,000, so it's just 1 with 3 zeros. So I'm just going to write this out as 1,000. Now we're going to go ahead and subtract the 10 on both sides. And then divide by 4. So we get x equals 990 divided by 4. And 990 divided by 4, you can actually reduce that. We can divide the top and bottom by 2, and that will be 445 divided by 2. Or 495, I apologize. Wait a second. Let me double check that. Yeah, this is actually going to be 990. Yeah, so this should be 495 instead of 445. So my bad. That was a little math error. So this is going to be B, 495. All right, so for number 3, or 29, we have 3 log base 2x equals 4. Go ahead and do that on this side. All right, and then again for this one, there is no base written, so we assume that it's an invisible 10. All right, so first off, we need to get rid of this 3 on the outside. So we're going to go ahead and divide by 3 on both sides. We'll do that first. All right, so now we can get rid of this log by using the base against it. So we're going to do 10 raised to both sides, and that will get rid of the log, giving us with 2x equals 10 to the 4/3 power. Next, we can just divide the 2 off and get our answer. So we can go ahead and plug this in. I'm not sure if there's a decimal tied to the problem. Yes, there is. So we're going to go ahead and do that on the calculator. So we got 10 raised to the 4/3 divided by 2. So 10.77. So it looks like it's A. All right, so now let's go ahead and solve the exponential equation. So now we have 4 to the 4x equals 8. All right, so how do we go about solving this? Well, we're going to go ahead, we got to get rid of this 4, right? So in order to get rid of this 4, I need to do a log, base 4. See, now these 4's match, so now I can cancel them out. I can only get rid of an exponential equation with a log. So now we got to do the log base 4 on the other side. We got to show equal treatment on both sides. So we get 4x equals log base 4 of 8. Then we got to divide by 4 on both sides. All right, so that's my x. X equals log base 4 of 8, which divided by 4. Remember that when you type this in the calculator, however, you got to do the log of the argument divided by the log of the base, and then we can divide it by 4. Okay, so we got to do for the numerator part, we got to do log of argument divided by log of base, and then we take that result divided by 4. And that's how we can do log base 4. Okay, so we're going to do that on here. So let's put that in parentheses. So parentheses, log base 8 divided by log base 4, close parentheses one more time, divide that by 4. we get 0.375. 0.3, let me double check the number here real quick. Okay, so if you wanted to convert that to a fraction on the calculator, you can use the math key. So you hit math, and then you hit 1. That's going to convert, see the little arrow with the fraction, so that then you hit enter, convert that to a fraction, and that will convert that to a fraction for you, which is 3 over 8. Okay, so 0.375 is the same thing as 3 over 8. Okay. All right, so now we're going to switch gears to geometric series and geometric sequences. So what is the sum of the geometric series rounded to the nearest whole number? All right, so what we're going to do, remember that the geometric series looks like this. Oops, this should be to the x power. The general form for the geometric series kind of looks like this, where you start at 0 and you go all the way up to n, and then you have ar to the x power. Okay, so that's the general form of the geometric series. Now, to find the sum of that, we use the formula. We use this formula. So Sn equals a1 times 1 minus r to the n divided by 1 minus r. So this is the formula to find the sum of the geometric series. So all we got to do is identify our a, or this is our a1 right here, identify our a1 and our r, and then our n, and then we can plug it in. Okay, so if you were to compare these two forms, you can tell that a1 is 2. So we're going to plug 2 into there. And then you can kind of tell that we have the r to the x power, so that's going to go there for r. And then lastly, we have our n. Our n is clearly the 15. So we're going to go ahead and type that into, or plug that into the sum formula. So we got a1 times 1 minus 1/2 raised to the 15th power, all over 1 minus 1/2. All right, and then we're going to go ahead and type that into the calculator, of course, carefully, making sure that we include all the parentheses here. So we have 2 times parentheses 1 minus parentheses 1 divided by 2 parentheses raised to the 15th, close, divided by parentheses 1 minus 1/2. All right, so we get about 3.9999, so about 4. Let's see, to the nearest whole number, so we got 4. All right, that's how we do the sum of the geometric series. So is the sequence given below geometric? If so, identify the common ratio. So all you got to identify, is it geometric or not? So geometric, remember, is when you're multiplying or dividing by the same number. So if you look at this set of numbers here, in order to go from 1 to 2, I got to multiply by 2, right? In order to go from 3 to 9, I got to multiply by 3. So basically, in total, I multiplied by 2 over 3, right? 2 over 3 times 1 over 3 is 2 over 9. If I continue that pattern, if I multiply by another 2 over 3, that will give me 2 times 2 is 4, 9 times 3 is 27. So this actually does check out. So yes, it is a geometric sequence. And what is the common ratio? 2/3. Pretty simple. All right, so what is a possible value for the missing term of the geometric sequence? So for number 33, we want the second term. So we want a2. So a2 is a question mark. But we do know a1, and we do know a3, right? So we should be able to find this. So what we're going to do is we're going to set up two equations for the geometric sequence. Okay, so I'm going to do number 33 down here. So again, we said that we know a1 and we know a3, and that's it. That's all we know. a2 is a question mark. So the formula for the geometric series or sequence is an equals a1 times r to the n minus 1 power. So what we're going to do is we're going to plug this formula. We're going to plug for a1 and we're going to plug for a3. So let's do a1 first. If I do that, I get a1 equals, oh, I'm sorry, they give us a1, so we don't need to plug it in twice. I apologize. Let me, because we already know a1. So we could just plug that in here. There you go. So that's what I meant. Plug in 54 into there. Now, they give us a3, so let's plug in for a3, not a1. So we get a3 equals a1 r to the, in this case, my n is 3. Okay, that's my n. So I get 3 minus 1 power. Okay, so now we know what a3 is, so we're going to plug that in here. And we know what a1 is, so I'm going to plug that in there. So in that case, I get 1944 equals 54 r to the second power. Now our job is to solve for r, so we're going to go ahead and divide off the 54 on both sides, and then we're going to take the square root of that. So we get this divided by 54 equals r squared. The only way to get rid of that squared is with a square root. So we're going to do the square root of that fraction there. So what is the square root? So to do the square root, you hit second x squared. So what's the square root of 1944 divided by 54? Turns out that it's 6. So we got r is 6. Okay, so we know r, so we can plug it in to get a2. Now we're ready to get a2. So a2 equals a1. Remember, a1 is 54. Now we can plug in r times 6 raised to the, remember now that's n, 2 minus 1 power. So we have 54 times 6 to the 1 power is our answer. So that's 324. And there's our guy. All right, so now this one is asking what is S7 for the following series. So we know A1. What is my R? Well, I know that it's going by -4. 6 times -4 is -24. -24 times -4 is going to give you 96. So our R here is -4. And our A1 is 6. So we're ready to plug that into the, or in our N here is 7 because we know that we're looking for the 7th term, or the sum of the first 7 terms. So 34 is actually pretty straightforward. So we're going to do S7 equals A1 times 1 minus R to the N, all divided by 1 minus R. We're going to take that, plug it into the calculator. Let's see. Oh no, let me erase the answer. And then we'll divide it by, make sure to put that denominator in parentheses. So that 1 minus -4 has to be in parentheses, like that. Okay, so we get 19,662. Okay, which is A. All right, so now we're going to go ahead and do number 35. So we're looking for S5 now. So we know A1 is 1,000. We know that the pattern is going by halves, right? So that this is times by a half. So half of 500 is 250. Half of 1,000 is 500. So my R is clearly going to be a half for that one. And A1 is 1,000. So let's plug it into the formula just like we did for number 34. So S5 equals A1 times 1 minus r is a half raised to the, in this case, n is 5 over 1 minus 1 half. Plug that into the calculator. Going to go ahead and delete that. Make sure you put the denominator in parentheses. All right, we get 19,000 or 1937.5. So it looks like it's C. All right, guys. That is it for the review. I hope you took a few things from this video, and I will see you in the next one.